Okay, so we have this double arrow lemma, and it allows us to basically understand the structure of Q double arrow R. Now, I believe that one can go deeper into this kind of structure of Q double arrow R in sets to the power of C, and probably uncover more results which make these kind of computations even easier. But this is still something we can use, and so let's have a go and see what these kind of objects look like for our category of functions. So here we have an object A. It has these vertices 1, 2, 3, 4, and these loops D, E, F, G, I. And I've just drawn in these sub-objects, little q and little r. And what we really want to do is to compute this sub-object Q double arrow R. So we're just going to repeatedly apply this kind of double arrow lemma. So basically we just pick an E-type element theta of A of E and then ask ourselves, is it true that doing theta under arrow after the pullback of Q along theta under arrow gives us something in R? And if it is, then that theta belongs to our sub-object Q double arrow R, otherwise it doesn't. Okay, so let's start doing this. Firstly, let's pick this E-type element G of A. And so we form G under arrow, that's obviously an arrow from hom E comma blank into A. And then we pull back Q along G under arrow. And that's going to give us a sub-object of hom E comma blank. And then I mean, really, we ought to be picturing this as a kind of sub-object coming out like that. But anyway, we sort of compose that with G under arrow. And essentially, we're just looking at this kind of composition. So really, we're just going to be sending this well, okay, let me draw this out properly just to be more precise. So the pullback of Q along G is now going to just look like this sub-object that just consists of S here. And so when we do this composition, G under arrow after this pullback, that's this composition of this purple arrow and this green arrow. And that's just going to be this arrow which just picks out vertex 2. Then we ask ourselves, is this in R? And the answer is yes. So G under arrow is in Q double arrow R. Or if you like, we could say G itself is an E-type element of capital Q double arrow capital R. Because we can think we're representing Q double arrow R as an inclusion monic. Here, look. Okay, and in a similar way, we're going to have that F under arrow is in Q double arrow R. Now let's do the same kind of computation for this loop D here. So we form D under arrow, then we pull back Q along D under arrow, we get a sub-object of Hom E comma blank. In fact, it looks just like this one. It's just the identity arrow. And then when we do D under arrow after this pullback, that's going to give us an object. Sorry, that's going to give us an arrow into here. But we find that that arrow is not going to be in R. And therefore, according to our result, we have that D under arrow is not in Q double arrow R. And this makes sense. I mean, we can think of Q double arrow R really as the kind of structure where if it's in Q, then it's in R. But clearly this loop D is in Q, but it's got nothing to do with R. So D under arrow is not in Q double arrow R. And similarly, E is not going to be in Q double arrow R. What about this loop I? Well, when we form I under arrow and we pull back Q along I under arrow, we just get the empty sub-object of Hom E comma blank, and then doing I under arrow after that is just going to give us the empty sub-object of A, and that's in R, okay, because an empty sub-object's always in a monic. And so we have the I is in Q double arrow R. In fact, in this particular category, oh yeah, and similarly we're going to have that 3 under arrows in Q double arrow R for similar reasons, basically because it has no intersection with Q. So we can always use this kind of method in general to sort of calculate this kind of structure of Q double arrow R. It turns out for this particular category of functions there's actually an easier way, because the thing is, for us, these arrows from Hom functors are always monomorphisms. Okay? When we have a loop in our category, under the Oneida correspondence, that corresponds to a kind of arrow like this green one here, which is just sort of pointing out a loop in A, and that's clearly a monomorphism. It's clearly one-to-one on vertices and loops. And so is the kind of arrow which just goes from a single vertex into a vertex of A, the kind of arrow from Hom V comma blank. So since all our Hom functors are monomorphisms, we can actually use another kind of result, another result from McLarty, to calculate Q double arrow R. Anyway, before I get onto that, let me just show you what Q double arrow R actually looks like in this case. You see, we basically have all of the loops and vertices except for vertex 1, because that's in Q but not in R, and this loop D here, because that's fully in Q but it's nothing to do with R, and also this loop E here, because that has something in Q but it has nothing in R. Okay, anyway, this result is very helpful for us for this particular category to really understand what's going on better. I mean, you can get there using this kind of approach, but it takes a lot of thought, whereas this is a nice kind of shortcut. So this is theorem 13.6 from McLarty, and it says that if we have a monomorphism S into A, then when is S in Q double arrow R? Well, since S is a monomorphism, we say when is S contained in Q double arrow R? And this happens if and only if S intersection Q is contained in R. In fact, it's interesting, this is kind of related to the fact that q double arrow r looks like an exponential object in sub A, but I digress. Anyway, to use this result, we just, like I say, we note that these arrows from Hom functors in this category of functions are monomorphisms, so we can directly apply this result. So basically what this is telling us is that a vertex is going to be in q double arrow r if and only if the intersection with that vertex with q is contained in r. Okay, so for a vertex, the vertex is always going to be in q double arrow r, except for the case where the vertex is in q, so this is non-empty, but the vertex is not in r. That's the only case when a vertex won't be in q double arrow r. In all other cases, all of the vertices will be present. Alternatively, if S is an arrow corresponding to a loop, well, that'll be in q double arrow r just as long as the kind of intersection of that loop with q is contained in r. So I think this is a sort of verbal summary of the structure of q double arrow r for our category of functions in general. The vertices of q double arrow r are all the vertices except those which are in q but not in r. What about loops? Well, a loop, if a loop and its vertex does not intersect q, so in that case S intersection q would be empty, in that case, of course, the empty subobject is always contained in R. So in that kind of case, the loop will be in q double arrow R. Okay, if it's nothing to do with q, then it is in q double arrow R. Alternatively, if just the vertex of the loop is in q, then the loop's going to be in q double arrow R if and only if its vertex is in R. Okay, because in that case, the intersection of the loop with q will just be the vertex of the loop, and so the loop will be in q double arrow R precisely when that vertex is in R. And then the other case is, what about if the whole loop is in q? Well, in that case, the loop's going to be in q double arrow R if and only if the whole loop is in R, because in that case, we'll have that S intersection, we'll have when S is the whole loop, S intersection Q will be the whole loop, and that has to be contained in R in order for the loop to be in q double arrow R. So I think this basically describes the situation. So you can use this kind of result if you're lucky enough that your category set to the power of C you're studying has all of these kind of arrows from Hom functors as monomorphisms. Otherwise, you can use this kind of approach to work out q double arrow R, or, you know, you can always just use the sort of definition of q double arrow R like this.